Sondre, it's great to see you in person again. I mean, we've met a couple of times now. It's always a great pleasure. What brings you to the Netherlands this week?
I'm here for the ASME B31.3 Code Week, which I've been looking forward to for a very long while now. Yeah. It's great being back in the Netherlands, and yeah.
Awesome. I mean, same here. Like this Code Week has been on the calendar for a while. How is the week going for you thus far?
I think it's amazing. It's awesome. You meet all these people, you know, you read about them, you know about them, and suddenly you get to talk with them, you get to listen to them, you got to learn from them, and you got to discuss with them. That's kind of what I really appreciate by being here.
Yeah, you kind of are able to put the face behind the names.
Exactly, the face behind the name, yeah.
Yeah, what I find interesting is also to see the system at play. I mean, you work with these codes, you know, B31.3, and there's this text on paper, but now you actually see how it, you know, comes into play. Did you attend any of the sessions?
Yeah, Monday, I attended the tutorial of the B31.3 with Chuck Becht. Yeah. It was a really good one, and I feel I know the code pretty well, but just listening to him, and there were some things when he said it, he kind of gave a different perspective on things, like some of the basic things even, you know, that's very interesting. And then, of course, I attended the session by Tony Paulin, which was very interesting as well. He was talking about new ideas and probabilistic approaches, like it's been common in the structural world for decades, how to introduce that into the piping world. So, and yesterday I attended the code committee meetings, which was interesting, as you say. Then you see the system at work, when it's working, and you see how they exchange ideas, how they discuss. Literally what we talked about yesterday will be in the next revision of the code.
I find it interesting. I mean, sometimes, you know, when you read a document like that, there might be a few sentences or even, you know, an equation or part of it of which you think, you know, okay, so that's what I'll use, but why and what are the nuances of why it is the way it is? That's something you see them discussing, you know, in those meetings, which I found very interesting. Maybe you can tell us a little bit on, you know, what are exciting projects and stuff that you are involved with at the moment, Sondre.
Of course. When I started Stressman, one of the main things with Stressman was that we were supposed to challenge the status quo. It's not always we manage to change the status quo, that's why we say we're challenging it. Something that's always been debated are flanges, leakage, and we found documentation and testing of American flanges, ASME B31.3 flanges, for example, but we found no literature on European flanges, like the PN16, PN40. So what we did now, together with the University of Southeast Norway, was to make a research project with them. So we got a bunch of students, they made a test rig, big test rig. When I saw it, I was like, wow, this is big. I saw it on the computer screen, it's like, yeah, that's doable. But you come there, it's taller than me, and it's pretty amazing. And we are testing right now, we only did 3 tests so far.
What kind of tests are we talking about?
We are pressurizing the pipe. So basically you have a straight pipe, a flange pair on the middle, and then this one is mounted onto the test rig. And then you're clamping it over here, and then you have a cantilever going out. So we are pulling down to generate a bending moment.
Yeah, is it closed ends?
Yeah, closed end. Yeah, exactly. Closed end, capped on each side. So we pressurize the pipe up to, let's say, that we are doing PN40 flanges. So we pressure is up to 40 bar. Yeah, got it. And then we start to load it. And then what will happen? We don't know. Well, we have an idea, of course. But then what will fail first? Is it the leakage, or is it going to leak, or is it going to burst, for example, or destroy the pipe?
Probably like buckling would be a risk, right? At the, I'm just thinking, I feel emotional leaking, but the next one might be buckling of the pipe segment?
To some degree maybe, but what we are seeing is actually a rudimentary setup. So we only can pull by 10 tons in the end of 10,000 kilograms, or roughly 100,000 newtons. So what you can pull down with to generate that bending moment. And what we've seen so far is that, of course, first we do the code calculations. We check what do we expect of bending moment before we have leakage or failure in the flange.
Yeah, which codes do you use, like the EN standards, I guess?
Yeah, we use the EN. First, of course, we do the Kellogg's method, which is hyper-conservative, but we just start there. And then we do the EN 1591, check.
Yeah.
And of course, we check the stresses in the pipe. And then we run the tests, and we see that the pipe is the limiting factor here. It's not actually the flange joint, but of course, we don't have a statistical ground yet to kind of say that that's applicable for all type of gaskets, for example.
Yeah.
So that's the next step. But now we just want to have a testing rig so we can repeat this experiment over and over again.
Yeah.
And we will use students to do those experiments because I think it's very interesting for a student to see failure mechanisms at play.
No, for sure. I can also imagine that you would change the piece of piping, maybe a thicker piece, just to see, where you get in the range where the flange actually starts failing and how it would start failing.
Exactly. So we managed to get one case where we had leakage before the pipe started to leak. And that was because we maxed out the bending moment. The bending moment capacity was reached, so we couldn't push that one further. So what we did then was to pressurize it from 40 bar up to 60 bar. And suddenly then you had leakage through the flange. And we have cameras around it, so nobody's allowed near it, of course.
Yeah.
And all of this is done at room temperature. The dream, would be to have this at elevated temperatures into the future.
And what are you anticipating for the research? Like, are you expecting that to be published into the public at some point?
Yeah, so we're going to share all of this knowledge. So we're going to be writing articles about it, white papers. Somebody who just want to discuss it, have questions, just find us. We like to talk about this stuff,
You mentioned the other day something that was on your mind related to, over-conservatism in designs. Maybe you can share your thoughts on that a little bit.
Yeah, it's something that I'm excited about to discuss because I see it so many times that our client or maybe the owner of the project are adding layers and layers of conservatism. So for example, you have a operating or a design temperature that might never ever happen. And that becomes the governing temperature of your system. And then you have pressures. It's the same thing. Maybe it's a short-term pressure. You're allowed with a higher stress for a short term, but not always that's communicated properly. So we use that occasional pressure as the design pressure. And then maximum temperature and maximum pressure doesn't need to happen at the same time, coincide. But you're doing that to calculate your wall often. Even though, like I learned yesterday at the B31.3 Code week from Chuck Becht, and it's written in the code, so I should have known it years ago. But it's like you take the pressure temperature combination that gives you the thickest wall thickness. That's your design. You don't take the maximum of the two and then calculate it. So, okay, what's the problem to do this? And this is only temperature.
Yeah.
For example, you have structural displacement. Maybe you have a tower that leans in the wind. Yeah. You have a ship sagging, hogging effects, or other reasons that you have these displacements.
Yeah, maybe also different departments within the company.
Exactly. And different design philosophies. The piping and structural has a lot of fundamental differences, how they're doing things, even though stress is stress in both departments, but how you derive to your safety factors and so on is different. So with structural, for example, okay, you get an envelope of displacements, and then you don't know, maybe some of it is from dead weight. Well, that doesn't really matter that much because it's not a cyclic load. Yeah. But we don't know if you just get a spreadsheet, use these values as input. Yeah, then we're cycling the dead weight of the system. Maybe it's a small portion, but it's still a portion of it. And then when you're stacking all of this together, your pipe in the end, because you use the maximum temperature together with maximum pressure, and then maybe notified body says that you need to use design temperature and pressure when you're evaluating loads on equipment, which I don't believe is correct. You should use the operating. That's another discussion. But then if you calculated over a big thickness, so you select a thicker pipe,
everything becomes stiffer and bigger.
Everything becomes stiffer. So if you have the same layout, you will wear out your pumps faster. You can overutilize your pressure vessels that you're connecting to, and it doesn't add value to the project. It doesn't add safety by being conservative necessarily. The pipe will never fail. But what about the stuff that you connect to it? Yeah. That might fail.
It might even overcomplicate, the design, the routing.
Exactly. And then, as you say, then you need maybe an expansion loop. and then maybe some spring hangers in there to carry some load because it becomes heavy. Maybe you need to go up a pressure class, you know, and you have a class 150 versus class 300 valve. That's different, you know. Valve weights are very different there, and every time you have to go this step upwards, then it just adds complexity that might not were needed there.
It's also a problem that's very much related to it's more of a operational problem, you know, having interfaces between departments, having, you know, safety factors being stacked one up, you know, on top of the other. I mean, is there a other way of doing it? I mean, those challenges are real, you know, in real life.
At least in our company, the way that we are doing piping, structural, pressure vessels, all of these things, but everybody in the company should know the lingo of each other. We should be able to talk. We don't have those walls set up. Of course, that might be difficult in a very big organization, but being aware of it, I don't know exactly how they could do it in a bigger organization. Maybe have people who knows both sides. Just as an example, when I started doing pipe stress, subsea pipe stress, I got the loads from the pipelines that was connecting to the equipment that was on the seafloor.
Like nozzle loads.
Yeah, so like nozzle loads, tie-in loads we call them. So they're huge, and you put that, and we use B31.8 in those cases, and we run the pipe stress analysis, and we check the stresses and whatnot. And then I was presenting, and I was very young at the time, I was presenting my results in front of a big group of people. Suddenly one guy standing up, okay, what load factor did you use? And I just froze. It's like, I don't know, should I use load factor? I use 1.0. And he got so angry that I didn't use load factors. Everybody knows that you have to use load factors, but no, you don't have to do that in piping. You have to do it in structural. So there's where you see, and suddenly he instructed me to go back, put on a load factor of at least 1.3, preferably 1.5.
So you mean like increasing the loads further rather than increasing the stresses further?
Yeah, so because what I realized after a few days, because I started looking into this, that there's two approaches. We use the allowable stress design approach. So you have an allowable stress. If you're within that allowable stress, based on that and that condition, you're safe. That's kind of the essence of it. But in that allowable stress, you already have your safety factors. B31.3 has a safety factor usually of 1.5 with respect to yield and 3 with respect to tensile. Yeah, there's more things in there. So, but that's kind of the very basic of it. So you don't apply load factors into there because that's taken care of. But if you go to structural, it's kind of the opposite way around. If you have a section 1 or section 2 member, steel member, then you can utilize the plastic capacity of that member. So you calculate the capacity there, or the resistance as some people call it, and then you apply the load factor, material factor, and all of that, and you calculate, okay, what do I get from my FEA or from my beam element analysis, and I compare that with the capacity divided by these factors. So it's a different approach, different mindset, but it's very dangerous when you take worst case scenario from both and mash it up to some kind of Frankenstein hybrid, you know, it makes no sense in there. You stack, suddenly I had 1.3 extra safety there in my analysis, which there's no need for. Because we are already within the code, and that was the goal here, to stay within the code requirements.
One way to think of it could be, you know, the more safety factor, the safer. So it's only economical loss, you know, so obviously that's a big argument. But on the other hand, I like your point just now that, you know, in some cases the equipment loads might actually become higher if you over-design everything and just make it stiffer. It's not always that you know, extra safety factors actually you know, reduce the likelihood of failure, perhaps.
No, exactly, and maybe the piping itself is very good because it's so thick and rigid, but then it's affecting everything around it. Maybe you have fatigue fracture in your structure or in your pressure vessel because you're overloading or you're much higher on load than you needed to in the first place.